So up until this point, when we are writing the formula for ionic compounds, what we've been using are cations, so the metals that you find on the periodic table, so cations because they are positively charged, and anions, which are negatively charged. You have positive in front, which is the metal, and then you have your anion, which up until this point has been the nonmetal, which is negatively charged. And then we cross charges to write the formula for the ionic compounds. All right, I'm going to add one thing right now because in addition to just simple anions that you find on the periodic table that are nonmetals, you can also have polyatomic ions. So this right here is a table of all of the different polyatomic ions that we will be dealing with. Now, what is a polyatomic ion? A polyatomic ion are covalently bonded atoms, and we haven't quite discussed covalently bonded atoms, but remember with a covalent bond, electrons are shared. So covalently bonded atom, covalently that have a net charge. All right. So I'm going to show you a couple of examples. By saying net charge, remember when we're dealing with ionic compounds, the net charge of an ionic compound is 0. But if you'll notice, if you look at all of these different polyatomic ions, they all have a charge. All right, so a couple of key things that will help you when you're identifying different types of polyatomic ions. The first thing, if you noticed, some of them have 8 endings, like sulfate. Some of them have ITE endings. If you notice, the only difference between an ATE ending and an ITE ending is the number of oxygen. So ATE has 1 more oxygen. So for example, this one has 4. This one only has 3. The other thing for you to know, if you see a per in front of the ATE ending, that means it has 1 more oxygen, 4, than just the ATE by itself. So for example, chlorate has only 3 oxygens, perchlorate has 4 oxygens. As far as the net charge is concerned, if you have a specific type of polyatomic ion and you're just adding oxygens, it doesn't actually change the charge. So for example, hypochlorite, chlorite, chlorate, perchlorate, they all have the same charge. And the interesting thing for a lot of these, for example, phosphate has a charge of 3-. That's the same charge as phosphorus or phosphide. So the important thing, because this kind of messes with people's heads a little bit, when you're writing, when you see the name of an ionic compound and you see an ATE ending or you see an ITE ending, know that you have a polyatomic ion. When we have the traditional, just straight non-metal like we've been doing up until this point, it has an IDE ending. Of course, there are a couple of exceptions to that. For example, hydroxide, which is located right here, that has an IDE ending, so just be careful, it's OH. All right, cyanide as well, peroxide. But for the most part, if it is a nonmetal on the periodic table, that's when you'll see the IDE ending. If you see an ATE ending or an ITE ending, then it's most likely going to be a polyatomic ion. Last thing about charge. Most polyatomic ions have a negative charge, either -1, -2, -3, or there's one polyatomic ion that has a positive charge, and that's ammonium. So all of the polyatomic ions, except for ammonium, will go behind the metal. Remember, positives go first, the cation, then the anion. So the metal will go before your polyatomic ion. The only exception to this would be ammonium, which would go first. All right, a couple other things for you to know. When you have a polyatomic ion, it is not going to exist by itself. It's going to form anionic compound. So let's practice with that right now. The first question on your practice, MgOH2, I have to name it. All right, and you'll see how it's super similar to what we've been doing. It's just one more added concept for you to keep in mind. And then we will write the formula for sodium sulfite. So for magnesium hydroxide, remember when you're naming a metal, if you can look at the periodic table and know the charge of the metal, you don't include the charge in the name as a Roman numeral. So magnesium, because it's an alkaline earth metal, I know the charge just looking at the periodic table, and therefore I don't need to include the charge in the name. So I've got magnesium. I don't need a Roman numeral, which is awesome. And then, as before, I'm just going to name my anion, my negatively charged ion. Now in this case, OH is not just one nonmetal like oxide or hydride. It is a polyatomic ion. Therefore, I would look at my chart, which of course will be given to you, and I see that OH is hydroxide. And so I just write that as the name for my anion. So it would be magnesium hydroxide. And that's it. All right? So, just as a review, nothing has really changed. If this had been O instead, you would have just written magnesium oxide. Instead, I've added one more component, the polyatomic ion, and so you just need to write the name of the polyatomic ion. You're not needing to put its charge, you're not needing to add anything else, change any endings, you're just writing what's given to you, what the name of the polyatomic ion is. So, here it would be magnesium and then just hydroxide. And the reason why we don't put a charge in the middle is because by looking at the periodic table, we know the charge of magnesium. Now I'm going to flip it, I'm going to be given the name, and I'm going to write the formula. So I'm given sodium sulfite. So I'm going to write out the two ions I have and then cross my charges. So sodium, Na, has a +1 charge. Sulfite, if I look up sulfite on my chart, sulfite, which is right here, has a formula of SO3, and it has a 2- charge. All right? So what I'm going to do, like I've always been doing, I'm just going to cross my charges now. So the 1 would be the subscript of SO3, the 2 would be the subscript of Na, and so when I write this, it would be Na2. Now remember, when I have a 1, I don't include that, so all I would write would be SO3, and I would be done. If I decided to change the problem on you just a tiny bit, and instead of sodium sulfite, if I had aluminum sulfite, I would again cross my charges. Aluminum this time has a 3+ charge. SO3 has a 2- charge. And I'm going to go ahead and cross my charges. So the 3 would be the subscript for SO3. The 2 is the subscript for Al. And so I end up with Al2. Here's why I included this additional problem. If you were to write it like we typically do, you write the name of the formula of your polyatomic ion, so SO3, and then you would expect just to put a 3 right after it, okay? Because you get the 3 from the charge of aluminum. Now, here's the issue. Right now, what I have written is that I have 1 sulfur and 33 oxygens. Instead, what I'm trying to say is that I have 3 SO3s. I have 3 sulfites. And so what I'm going to need to do instead, so that this 3 can be distributed to the sulfur and the oxygen, I need to put this polyatomic ion in parentheses. All right? Now, the reason why I put that in parentheses is to make sure that that 3 is distributed to the entire SO3. If I'm given this, the reason why I don't put this SO3 in parentheses is because it's implied that there's only one of them. As soon as you get 2, 3, or 4 of them, then you would need to put it in parentheses. So as soon as you need a subscript for a polyatomic ion, so for example, if I had here, the reason why there are parentheses is because I have a subscript of 2. If instead I had NaOH, I don't need parentheses around my OH because there's only one of them. All right, and that's all there is.